Welcome everybody. We're going to get started with this presentation about Thread, which you may know or might not know already. So we're presenting basically not much about the Thread protocol today, but about the open source project that's associated to it. So I'll first hand it over to my colleague. Saurabh, do you want to introduce yourself?
Hello, everyone. I'm Saurabh, and I work as a part of the open source group in Samsung Research America, and I'm based out in Mountain View, California. Before Samsung Research, I was working in SmartThings, which is another division of Samsung. And I was working in SmartThings for the past 12 years. And I was mostly working in the firmware team, working on we started with the Zigbee hubs, and I was working mostly on the Zigbee protocol and the end-to-end cloud connectivity with the SmartThings platform. And before SmartThings, I was working in Marvell Semiconductor for a good period of almost 10 years. And I started my career with NXP Semiconductors in Eindhoven. So I was working mostly on the TV chips and stuff like that. But for the past 15 years, I've been mostly working on the IoT technology.
Okay, and my name is Esko Dijk. So currently I'm working independently, but mostly for a Thread group, which we will tell more about later on in this presentation. I've been active in basically low power IoT devices already from around 2012. Also joined work in the IETF, the Internet Engineering Task Force that defines protocols for these type of devices. And I'm based in Utrecht, which is pretty close to here, sort of mini Amsterdam without the mass tourism. So you could visit it as well. Very nice city. And I'm now also active in specification, testing, development, and writing software for Thread. So we'll get started.
Yeah. So we will divide the presentation into the first half. I'll present the basics of what is Thread networking technology, and just try to touch upon how the implementation of this Thread technology goes into the open source implementation, which has really accelerated the consumption of the Thread technology into consumer devices. So it's not only in the home, but also in the commercial buildings, as well as commercial lighting applications. And then I'll hand it over to Esko, who will go deeper into the OpenThread repository, network simulators, and more on the testing side of how you can test the protocol. So the first thing is what is Thread? So as you know that in the world of the connected devices, there are basically two kind of networking technologies which are prevalent. On the one extreme, you have the old, reliant, powerful network technologies which are based on internet protocol, which is typically the Ethernet or the Wi-Fi. And on the other extreme, you have the low power, wireless, mesh network technologies. And the three most common ones are the Zigbee, Z-Wave, and the Bluetooth. Now, the Thread networking technology is uniquely placed between these two extremes, where the Thread networking technology is built ground up to be a low power mesh networking protocol, as well as it's also built on the internet protocol. So, but with this kind of uniqueness, what happens is typically every device or every node on the Thread network can have a native IPv6 address, which makes even a small device like a battery-powered sensor to be like a first-class citizen of the internet. So what a typical Thread mesh network looks like is, so if you see the uniqueness of the Thread network, if you compare it with hey, I already have a Zigbee network in my home, why do I even switch to a Thread network, is something which is very unique for the Thread network, that it is robust, reliant, as well as it's a self-healing network. Now, so the basic communication, what happens between all the nodes talk to each other, relaying the messages, which basically boost the network strength. Like you will hardly find like dark spots in your home or like any commercial establishment. The reason why it is so is because if you see all the thread mesh extenders, you can imagine them as like the main power devices. So typically in the home, if you have like the outlet or the plugs, they act like an extender and they boost the signals. And the crux of the mesh thread mesh network is like the thread border router. So basically, the function of the thread border router is to act like a gateway, which provides the connectivity between the backhaul Wi-Fi or the Ethernet connectivity in the home and the wireless connectivity, which is predominantly on 802.15.4 network. And the last one are the leaf nodes, which are typically all the sensors or the battery power devices. So why it is called a self-healing network, which is only the the most unique feature of the thread network is like even if a node or a device fails to function or it's like a dead, so you don't have a kind of a dead spot on that particular node. What happens, the protocol itself finds out an optimal route to route the messages. And basically there is nothing called like in a if you see a Zigbee network, you have a central Zigbee coordinator and you don't have this facility of like a self-healing. So if there is a kind of a node which is like dead, then basically like that particular part of the mesh is like a dark spot for you. So these kind of things are like special features of the thread network. So this is like going a slightly bit deeper into what an IP stack of the thread network technology looks like. So at the bottom, you have the typical 802.15.4 PHY or the MAC, which is supported by a lot of silicon vendors, and basically it caters to like the low power wireless protocols. So same PHY or the MAC can also be used by like the Zigbee and the Bluetooth, and most of the silicon vendors do have like all the stacks running on the same SoC, and they do some kind of a time multiplexing based upon which stack is needed at which stage of like operation. Like some part of the stack would be used only during the time of like commissioning or the pairing of the devices, and then you can shut down the stack, and then you can use another stack for like the basic operations or the communication between the devices. The 6-low WPAN is the most important layer for the thread IP stack, which is basically an abstraction layer. So what it does is the most important function is the header compression, and it does the fragmentation and the reassembly of the packets. And because of this particular layer, you can have each and every node can have a native IPv6 stack running on them. So basically all the nodes or the devices on the thread network will have IP connectivity. And above that, you have the standard UDP, TCP, and the V6 routing layers, which are all wrapped up in the standard security and the commissioning protocols, which are used like industry-wide. So now where does the thread group comes into the picture? Now, the thread group, the mission of the thread group is to provide a reliable, open, and a secure wireless networking technology so that more and more connected homes can have like diverse ecosystems for different kind of, suppose like you can have different ecosystems. You're not tied to a particular like ecosystem. You can have different ecosystem and to provide a good interop between the different ecosystem. That's one of the missions of the thread working group. So what we do is we generally educate the market. Like suppose there are some markets like the lighting industry or the commercial building industry. If they have been using like a proprietary technologies, we go to those markets and try to educate them what are the benefits of using the thread technology as compared to using the proprietary ones. And the most important thing what the thread group undertakes is the certification. So we have our own test labs which certify the devices both as a system as well as like a component. Now, the system will typically be like a thread border router, which goes into a larger embedded system. You can imagine, like, suppose most of the Samsung TVs or like the dishwashers or the refrigerators now have like a thread border router functionality. So all it wants is some kind of a Linux operating system running on that system, and then you need a 15.4 radio. Now, either you can the 15.4 radio can directly be embedded into that system, or sometimes you can even retrofit and make any embedded device like a router or a gateway as a thread border router by using a 15.4 dongle connected to the main embedded device. So regarding the specification, like we started in like 2015, where we had the release of like Thread 1.0, and as you can see, like we have had like regular cadences of releases, clearly showing that we talk to people in the market, we talk to the developer community, and try to gather like kind of what are the missing features, or what are the features which can be improved, or entirely new features which are not part of the specification. And we have been constantly working on those specifications to be included. So the latest version of the thread specification is Thread 1.4. And like, yeah, the regular cadence is probably like 2 to 3 years. If there are bigger features, then definitely it takes more time to release a new one. Otherwise, the regular cadences are almost like 2 years. So this slide basically shows where all thread technology is currently being used. So there's an alliance called a DALI Alliance, which is like the most popular alliance, which is used for commercial lighting applications. So what they have used, what they have done is they have decided to use Thread as the underlying networking protocol, and they develop their own specific application layer which caters to that particular industry. Similar to that, there is another IoT protocol called KNX. So KNX has also chosen Thread as an underlying low-power wireless protocol, and they are into all commercial building and MDUs. And of course, and I think most of the people would have heard about Matter. So Matter is very popular in the consumer space, where it's an application layer protocol, and the only wireless protocol they have chosen for the networking layer is the Thread. Apart from that, they use the Wi-Fi and of course like the Ethernet for commissioning and the control of the devices. So with the launch of the Matter, definitely. Because most of the major ecosystem providers like Google, Apple, Samsung, and Amazon came together to jointly work on the specification and the SDK, the Thread networking technology has gained a lot of momentum because of being incorporated in Matter. So now we come to the real crux, that what is an OpenThread project? Now, the OpenThread project is an open source project which basically is the reference implementation of the Thread specification, as well as it also provides various tools to develop the Thread protocol, as well as to test or simulate certain features in the scenarios where you do not have like real devices, or suppose like you don't have to wait for like a device manufacturer to like spin out a silicon and then do the testing and then deliver you the device. So pretty much most of the testing you can do using a lot of testing tools, as well as the network simulation. So typically, like any other open source project, it's also hosted on the GitHub. Initially, it was funded by the GitHub Enterprise was funded by Google. It has all the features of a typical open source project, which is hosted on a GitHub, like GitHub Actions for CI/CD, and anybody can post any kind of a suggestion, issues, or like a pull request on this GitHub, and the Thread working group actively looks at those issues and discussions, and they bring those back to the technical committee or the marketing committee for the discussions. The OpenThread code follows the BSD3 clause, which is very permissive, friendly. You can use, modify, integrate the almost most of the code without very limited restrictions. So in that, this is the main reason why it's very easy for even the hobbyists or like people who are working in university research to use this technology. And that's why it's gaining a lot of momentum, even for like startups and other smaller companies. So this is the list of like some common, like very popular silicon vendors who provide that thread stack running on their 15.4 chipsets. So you see mostly all the major silicon vendors. So these silicon vendors either make like end devices which only act like as a child, like your sensors or any other like outlets, whether it can be main powered or the battery powered. And then there is a whole lot of the same silicon vendors who work closely with big ecosystem providers. Like if you see Apple HomePod Mini, or if you see any of the Samsung TVs or the Alexa speakers, all of them have like a 15.4 radio inside them. And even now the iPhone 16 has an embedded thread radio inside that. So pretty much all of these silicon vendors work with these big ecosystem providers to make sure that the thread border router functionality works on their system. So yeah, that's pretty much now. We'll do a deeper dive into the architecture of the OpenThread, and Esko will cover the network simulation part of it. Thank you.
Yeah, thanks, Saurabh. So this is just to show you a bit about different deployment options. So when you have the OpenThread stack, you can basically build that in different ways. So there is at the left, basically one simple way to build it is to do everything in one code base running on one processor. So that's the single SoC option. But it's also possible to make splits. So if you have a two processor setup, you can split OpenThread in various ways. For example, in the middle, you see the OpenThread core is located on a radio SoC, while the application, so which could be a bulky application, or even a part of the IP stack, is on a host processor. This could be, for example, a Linux processor. And in between, there is a protocol, so that's defined already a couple of years back by OpenThread. So that's serial type of communication protocol that it's made to be as efficient as possible to do all the OpenThread interactions that are needed, basically. So that's also part of the project. On the right side, you see something similar, but now the core has moved to the more capable processor. And the radio SoC on the bottom is just doing a very small part. So it's just including radio drivers and sort of minimal what's needed API to perform all the OpenThread radio operations. So OpenThread as a project, it's a C and C++ code base. It defines a number of APIs. So we follow particular standards that have evolved. So usually the public APIs start with OT and then something. So it's a module name and a function name. And that's made to be compatible with C99, so that all C applications should be able to use that. Even if you have C++ applications, so that should not matter. So it's defined to be as standard and simple as possible. And the core of OpenThread uses C++ without using any standard library. So if any utility-like functions are needed, it's defined internally itself. So this was done to get a minimum code size to be able to run on different kinds of embedded processors. So some of them have, for example, little RAM and low flash. So it should be possible to run on there too. Then there are platform APIs. So that's basically OpenThread stack calling into the platform. So this is what the vendors provide. And the vendors of the various chips should implement that API. So they can, be, for example, signal capabilities to the OpenThread stack, or OpenThread stack can do elementary operations like, okay, send this radio packet now. And I don't intend to go through this one in detail, but I've included it for reference in the slide deck, so you can also download it via the schedule website. So you also nicely get all the clickable links then, which are also coming up later in this presentation. This is just to show that OpenThread provides layered architecture. So we have various components, basically, and those are organized into directories. And these directories are kind of symbolizing layers. So there are particular groups of functionality that are used. For example, all the Mac layer things. So that's basically the medium access control for the radio is in its own folder. And there's its own set of files. So basically, the Mac is implemented in OpenThread, so it can basically do kind of optimized things and also some small changes that Thread did to the 802.15.4 specification. But it's also possible to rely on the Mac capabilities of the radio chip itself. So if it has those capabilities, then OpenThread can be configured to delegate that those Mac operations also to the chip to some degree. This is about the build system. So there is a build system in place. It used to be more extensive, now has been simplified a bit. So the main one that's used is CMake together with Ninja. And that's also configured basically by the scripts that are supplied there. And there's also the build.gn makefile system, which I never used. So unfortunately, I can't tell much about this. I think it's used for Android, but for the rest, I don't know much about that. It does have basically configurability also in the build system. So at highest level, there are 3 important configurations. So what type of device you want to build. So we have a flag to build an FTD, a full thread device, an MTD, a minimal thread device, and an RCP, which is a radio controller, basically. So that's the most minimal version of Thread, basically. So it will not have a stack inside, but it will basically accept commands from an OpenThread stack running on a more capable processor. FTD and MTD are basically concepts defined in the Thread specification. So minimal, you can imagine it uses less code, less memory. It's used for the cheapest type of Thread devices, like a small window or door sensor that runs on a battery. So it's also the most battery efficient type, but it cannot help in routing mesh packets. Okay, this continues a bit on the configuration options. So there is a sort of structure to those. So conventions are followed. So you can enable and disable features, and there are really a lot of them. I'm sometimes surprised myself, like how much you can configure. It's a lot for testing purposes, or for tuning OpenThread to use less memory. The downside is that if you start tweaking with these options, you might lose the, let's say, compatibility to the specification. So your product might not be successful in the product certification. So what we also have is projects that define the recommended set of flags to basically get your product compliant to the specification. But if you don't want compliance and you just want to tinker around with it, that's also possible. So you can use any of these settings. So OpenThread also proposes improvements that way. So things they add, which are not spec compliant, but are even better actually. So that feeds back into the spec development. So it kind of goes in both ways. Logging, just a brief bit about logging. So we have defined different log levels. These can be statically configured. That's the usual case. There's also a feature to do dynamic logging so that you can dynamically change log levels during operation. So that's typically not used in products because it adds extra code, etc., extra time. But it could be useful for debugging or your own product development process. Logs can go to multiple places, so like to a CLI if you have one, or to the serial, or you can write your custom logging handler, basically. And then one particular component I want to focus on, so this is part of the overall OpenThread project. We have many repos. So one of the subtopics there is the OpenThread border router. But to basically introduce you to that, I first have to tell you about the thread border router. So this is a formal role defined in the specification. It's basically the interface between the high-speed IP network, like your home router, for example, Wi-Fi Ethernet, and the thread mesh network, which is very low capability. So its links are 250 kilobits per second. So it basically cannot handle the bulk of traffic that would be possible on Wi-Fi and Ethernet. So it has to do something. Well, a couple of things it does. It's like ingress filtering, but also the 6LoWPAN compression. There is some aspect of even IPv4, IPv6 translation. So that means that thread can still work if your home ISP only provides IPv4, for example. So there is no IPv6 at all. So it can still work. So the border router then does the translation. And the nice thing about the thread border router, it's not application specific. So it's not a gateway that translates application commands, but it's just, basically moving IP back and forth, which could contain anything you like UDP, TCP on top of it with any higher layer protocol. And Saurabh already mentioned about the Samsung products. So there are various vendors with products that are already thread border routers, basically. The question is, are they also OpenThread border routers? Well, that's maybe more difficult to answer. OpenThread border router is at least available. So it's an open source project, and it provides a reference implementation of a thread border router that we also use for certification testing and in general to see if a product is kind of compliant to what we specify. And that's typically built on the Raspberry Pi. That's the default build with the USB dongle added, which can be one of several vendors, I think. And there's a guide on OpenThread.io, the website for that. So there are many guides there. The only slight problem is that some of them could be out of date. So we have a bit of a maintenance problem, I think, with the documentation here, but that probably sounds familiar to most people here. But there is a project linked here to have a scripted install of the OTBR reference release. So that's basically a kind of all-in-one lengthy build process that basically builds for Raspberry Pi and a particular hardware dongle. And that's what I have used, and that works at least best. The benefit, of course, of building one yourself is that you can tweak things. You can try new software, so like new stack features in OpenThread, and see if they work. And you can also do logging or CLI access, which you usually don't get in the commercial product. Or maybe you can. You do actually in some, but but CLIs are always dangerous here, especially the OpenThread CLI, because some commands just make your device immediately go out of spec. And I always try to add warnings in the documentation about that. So I'm the guy who makes pull requests with warning, don't use this CLI. So hoping people would read it. But testers love it, of course, and people at home tinkering with it as well. So we'll see how that goes in the future. And another component I would like to briefly focus on is the OpenThread network simulator. So this is one I've been working on the development. So I'm not the original author of that, but I started at some point because of interest. So the idea there is you have a simulator to simulate an entire network of multiple OpenThread nodes. So you can see in the picture, every shape there is a node of different type. And they're basically fully operational with a complete OpenThread stack and CLI, each of them. And the nice thing is here is you can make it run faster than real time. And the nodes will not notice that, of course. So they think it's real time, but it's not. So you can easily go like 100 times faster, for example, for a not too big network. And if needed, you can also run multiple firmware versions on that. So if you have basically different stacks. So you provide the source code, you do a specific node build for the simulator, and then you can load that node in the simulator. So it's basically compiles into a Linux executable or macOS executable, which interfaces to the simulation. So instead of a radio driver, there is a virtual radio driver there that will talk to the simulator. And so that way you can also test multiple thread versions. So if you take like a historic code base, like 1.1 or 1.2 or 1.3 thread code base, you can also load those nodes in and do more testing, like see if is the new code compatible with the old one, for example. And this is useful for things like continuous integration testing, which we do in OpenThread. So then if somebody makes a change, then this would basically, as part of the CI test, load an instance of the simulator. In fact, it even builds a simulator. That's, I think, a bit inefficient now, but hopefully it will be improved. So, but it performs a whole suite of simulations then with basically these node builds. You could also add historic legacy node builds in there to see the interaction. And then when all the tests are green, basically, then you don't notice anything of that, but you just see the green check marks. So then you know the change is okay. I will tell a bit more about the network simulator now. So what does it do? It accurately models radio chip timing. So that's an aspect I have added over the last couple of years. So including things like things from the 802.15.4 protocol, CCA backoff, and also potential interference between radio nodes that are close by, also depending on how far away they are, RSSI, things like that. And you can load different radio models there, like one that looks like an indoor model or an outdoor model, which are pretty different. And this is interesting from a coding perspective because multiple languages are used. So it's using Go for the simulator core, which is really a nice language, I think. Also C and C++ for the simulation platform. So it's basically the, let's say, the virtual radio driver that the OpenThread stack uses. And there's Python 3, which is used for scripting and examples. And there's a Python binding as well. So you can script your own experiments. You don't need to interactively be running the simulator, but just run the script. Okay, good thing about simulated nodes is that it can be much faster, of course, to integrate into your development cycle. So you just build, deploy, and run much faster than you would on actual hardware, just because of the time speed up, but also no need to program things or flash things or have electronics on your desk. And we found over the past time that also corner cases will pop up in the simulation. So it's not like, yeah, you will only see issues when deployed in a real radio hardware, but you will also typically see most of the issues already in the simulation, basically. So that means bugs are also faithfully reproduced, which is good in this case, because you want to find them before you put this code into your hundreds of hardware nodes and spend days running your network and finding only then that you made a stupid mistake. So this will catch it much earlier. You can also do other things like look at logs more easily. So because it's in simulation, you don't have really a size limit on logging. So you can just say, okay, please enable all logging on every level, every module by default. And you can see it. Of course, the downside of all this is that it does not accurately simulate processing delays. Like, for example, running a complex crypto operation might take time. And this is something that the simulator currently cannot do. It just assumes it happens in zero time. Basically, it's as an event-based simulator. So only the radio operations and timer-based operations are accurately modeled, but not things that take actual processing time, like so many microseconds. And then this is just to show that you can use Wireshark for IPv6 and traffic analysis. So that works for the real thread networks where you do capture radio traffic, for example, and decrypt it. It also works for the simulator. So basically it uses a well-known encryption key. So every time you load the PCAP file in Wireshark, you immediately see what's going on. So that's also very useful because you can do things like filtering to see your specific message, like, okay, where is my co-op message? So you just filter on co-op, for example, and then see them pop up. And you can also check are the fields, for example, compliant to the IETF specifications for those protocols. And when I look at it, usually I see something that's not compliant. So I'm very good at finding these non-compliance issues, because I also work on IETF protocols myself. Getting started with OTNS. So at some point I've done with a few people some mini workshops like, okay, how to get it installed. It's still a pretty lengthy process. Takes a lot of hard drive space as well. There is now a better, almost automated scripted install that should work, but not always. It depends on specific versions of like Go and Python languages, and that can cause some trouble if you're on an older operating system. What does work is a Docker playground, so that's probably the easiest way. So I see that, I see this is the old version of the slide. So the new versions has slightly more parameters and does have a working GUI. So the one you can download will be the good reference for that. You can also come to me after this talk, because it's a lunch break, so we can check it out. So that's an easy way to run the simulator and play around with it. So not to do serious things, but just to get a feel of it. And the good thing is that any learning from the simulator, like if you'd use the CLI, for example, or all the concepts, all the names directly translate to things you can use on real thread networks, because everything is exactly the same, of course. So you can start learning about thread without doing a hardware investment initially. So this is just a picture I took from the code lab. So this is the link here, available on OpenThread.io. So it's like, I think, roughly 1 hour tutorial, which makes you install the simulator and use it. And this highlights some of the concepts that I use. So different graphic elements are used for different types of devices. So there are basically subtypes of the two that I mentioned before. So that can make it a little bit more complicated. And this is the GUI part. There's also the CLI part. And the nice thing about this tutorial is that you get, all the time you load it and you scroll to the end, you get a new learning badge. So we're starting to get pretty annoyed after 20 learning badges, but okay, you have to tolerate that. Okay, and then this kind of gets to the end. I still wanted to basically show the simulator, so maybe I can just briefly go there. Oh, it says connect to Wi-Fi. Yeah, so just started here, OTNS. Let's see if it's readable. I'm not sure if it's readable. I can make it larger, of course. So you have to like these buttons like add a new router, which is the technical term for a mesh extender. So we used to call it router. So that's a device that can basically route packets on behalf of others. So you start one, it sees there are no peers. So I become the leader. So it's kind of the administrator for the network. So you can this way add more routers and they will basically detect and connect other types of devices as well. So these are the minimum thread devices, so they're not capable to route, but need a parent, as it's called, to do their routing business for them, and they find a parent here as well. And here, currently it runs at 1 time speed, but you can also speed up the simulation here, like, so I want time to go fast, so we now go at 64 times, so you see more of that stuff happening. This are also border routers. This is also interesting. So it doesn't interface yet to actual IP Ethernet, for example, but there's somebody working on that. I hope that we get this contribution in this year, so you can actually interface to real Ethernet or Wi-Fi backbone, basically, and also to physical thread border routers there. So they would recognize this simulated border router, hey, that's a real peer, and connect to it as well and form the thread network. So that will be interesting when that extension comes in. Okay, there's lots of things happening here. So there's also CLI here, so you can type help to see things. You can list the nodes, and you can also go to a particular node. So that's node 3 here. And now we have an OpenThread CLI, so it's just the same as the hardware device. So you can do things like version or type like, for example, router table. So you see what is your routing table, what are all the devices. Yeah, state is another thing, so you can see what it's doing here. There's also things like transmission power. So because it's a simulated device, you can use arbitrary transmission powers in dBm. So it will also translate to the radio simulation that way. So it becomes a stronger transmitter here. Yeah, maybe logging is also important. So there is some logging to files. There's also watch feature, so you can watch a particular node. Oh, I should do that. Not in the CLI, but in the simulator CLI. So there are 2 levels of CLI here. So you get a lot of these log messages here. But usually it's easier to see that in the log file and then process it in an IDE, for example. And then finally, there's the Wireshark part. So this is, for example, here. So you can, let's see. Yeah, open recent should work. Open recent, yep. So this is the one basically of the simulation that's currently running. So you can also already look into that. So you can basically decide to see all messages here that are being exchanged. Let's see. Oh, wait. Should maybe go down. So you see messages here, and there's currently quite a lot of that because it's running at high speed. So you get that. And you can also see co-op messages, for example, being exchanged. So this is used by application traffic, which uses co-op sometimes, but also by the thread management traffic, which uses co-op to basically, create the structure of the mesh network. So you can look into that. Okay, then maybe back to the slides. So we're of course always looking for contributors who like to work in this area. So then your code can help build the future of IoT. Once the code gets into OpenThread, of course, which is not particularly easy because there's all these checks and processes that we have. And usually the main contributor comes back saying, this doesn't fit in our architecture, so it's better to discuss that up front. I see a lot of people sending in big PRs without doing the talk up front, which is usually, maybe not the best way to get the code in. And there's also some of the companies actually have people on the payroll working on these features. So we might have opportunities there as well for people who want to work in this area or that work on a project basis. It does take some time though to get basically used to the OpenThread coding style and the architecture. So because it has evolved over the past 10 plus years, so it's getting pretty complex. So with that, I want to invite you to come have a chat or a small demo during the lunchtime. And there's also still, I think, how many minutes for questions? 3? No? -3? -3. So, feel free to come here. Thank you for your attention.